The hidden crisis in modern medicine. Why almost nobody measures their hormone levels during their lifetime, yet it's absolutely required to understand health problems and fix weight issues. Hormones are the master regulators of every biological process in your body, yet we treat them as invisible until something goes catastrophically wrong. Let's quantify exactly how severe this problem is in modern healthcare. Here's the shocking reality. Approximately 99.7% of the global population never gets comprehensive hormone testing during their entire lifetime. Only 0.3% do. With a global population of 8 billion people, only about 24 million people have ever had comprehensive hormone panels done. That's roughly the population of Australia. Why is this such a critical problem? Let me demonstrate with a concrete example. Major hormones like thyroid hormones T3 and T4, TSH, cortisol, testosterone, and estrogen all emanate from central control systems and affect every cell in your body. Let's examine how hormone dysregulation directly causes weight problems that diet and exercise cannot fix. Consider this relationship. As thyroid function declines, shown in pink, body weight shown in blue increases, but not in a simple linear way. There are complex feedback loops. Let me pose a question. How much does thyroid hormone actually affect your basal metabolic rate? The answer is dramatic. Your basal metabolic rate changes by 20 to 40% for every doubling of free T3 concentration. A person with normal thyroid function burning 2,500 kilocalories per day might drop to only 1,500 kilocalories with hypothyroidism. That's a 1,000 kilocalorie difference. Over 1 year, this deficit equals 1,000 kilocalories per day times 365 days, which equals 365 megacalories, translating to approximately 47 kilograms of potential weight gain, using the conversion factor of 7,700 kilocalories per kilogram of body fat. Now let's address an even more subtle issue. Hormones fluctuate dramatically throughout the day. Cortisol, the stress hormone, follows a strong circadian rhythm. It peaks at 6 to 8 a.m. at around 400 nanomoles per liter and drops to 100 nanomoles per liter by midnight. This means that a single blood draw at one time point is nearly useless for understanding your true cortisol status. The same person measured at 8 a.m., noon, and 8 p.m. would show vastly different cortisol levels, yet current medical practice relies on single snapshots. Let's calculate why traditional hormone testing is prohibitively expensive for continuous monitoring. A comprehensive hormone panel costs between $500 and $1,500 in most developed countries. For proper monitoring, especially during intervention, you'd want at least weekly measurements. This means annual costs of approximately $52,000, which is simply not feasible for 99.9% of the population. The cost barrier means only about 2% of people who need regular hormone monitoring can actually afford it. This is where lab-on-a-chip technology becomes revolutionary. Let me explain the physics. A lab-on-a-chip is a microfluidic device that integrates multiple laboratory functions onto a single chip, typically just a few centimeters in size. The key principle is that miniaturization fundamentally changes the physics of fluid flow and chemical reactions. The Reynolds number, which characterizes fluid flow, equals density times velocity times length scale divided by viscosity. When you decrease the length scale by 1,000 times, the Reynolds number drops by 1,000 times, meaning flow becomes laminar and predictable. In microchannels, different fluids can flow side by side in parallel laminar streams without mixing, allowing precise control of chemical reactions. How do these chips actually detect hormones at such low concentrations? Let's examine the mechanisms. Typical hormone concentrations range from nanomolar to picomolar, that's 10 to the negative 9 to 10 to the negative 12 molar. One detection method uses gold nanoparticles functionalized with antibodies. When target hormones bind, the optical properties change measurably. The peak wavelength shifts when binding occurs. Lambda peak equals lambda 0 plus delta lambda from binding events. Modern plasmonic sensors can achieve detection limits down to femtomolar concentrations, that's 10 to the negative 15 molar. The chip surface is coated with receptor molecules. Hormones from the sample bind specifically, and the binding is detected optically or electrochemically. The next revolution is integrating these sensors into wearable devices for continuous monitoring. A wearable microfluidic sensor might be integrated into a watch or patch. It continuously samples interstitial fluid through microneedles or sweat through pores. You might ask, why measure interstitial fluid instead of blood? The answer is that interstitial fluid equilibrates with blood plasma in about 5 to 15 minutes, giving real-time information non-invasively. Microneedle arrays penetrate only 500 to 1,000 micrometers into skin, collecting interstitial fluid which flows to the sensor chamber for analysis. These needles are 500 to 1,000 micrometers long, below the pain threshold but sufficient for fluid sampling. A critical engineering challenge is power consumption and wireless data transmission. Total power consumption equals sensing power plus processing power plus transmission power. Typical power consumption for these devices is 1 to 10 milliwatts for continuous operation. A lithium polymer battery of 100 milliamp hours can power the device continuously for several days before recharging is needed. Battery life equals 100 milliamp hours times 3.7 volts divided by 5 milliwatts, giving approximately 74 hours of continuous operation. Data is transmitted via Bluetooth Low Energy to a smartphone, which processes and displays hormone trends in real time. Now let's discuss the critical issue of accuracy and clinical validation. For clinical use, we require coefficient of variation less than 10% compared to gold standard laboratory methods. This correlation plot shows excellent agreement between lab-on-chip measurements and traditional laboratory assays, with data points clustering tightly around the identity line. Current devices achieve R-squared values greater than 0.95 for hormones like cortisol and testosterone, indicating excellent correlation. Let's examine concrete practical applications that are already being deployed. 3 major applications are continuous glucose monitoring for diabetes, hormone optimization for weight management, and stress monitoring through cortisol tracking. Continuous glucose monitoring has led to 100-fold better glycemic control compared to fingerstick measurements, providing a model for other hormones. Continuous glucose data over a week reveals patterns that single measurements would completely miss, enabling precise insulin dosing and dietary adjustments. Let's perform a rigorous cost-effectiveness calculation comparing old versus new technology. Traditional laboratory testing costs about $52,000 per year for weekly measurements. A lab-on-chip device costs about $200 initially, plus $20 per month for consumable reagents. Total annual cost is $200 plus 12 times 20, equaling just $440 per year. This represents a 118-fold cost reduction, making continuous hormone monitoring accessible to the general population for the first time. The cost reduction factor is 52,000 divided by 440, approximately 118 times cheaper. Modern chips can measure multiple hormones simultaneously through multiplex detection. A single chip can have multiple detection zones, each functionalized for a different hormone: thyroid hormones, cortisol, sex hormones, insulin, leptin, and more. Current state-of-the-art devices can measure 8 to 16 different hormones in parallel from the same sample. Raw sensor data requires sophisticated signal processing and machine learning for interpretation. The signal over time equals baseline plus periodic components plus noise. S of t equals S0 plus A sine of 2 pi ft plus eta of t. Noisy sensor data can be filtered and analyzed using machine learning algorithms to extract meaningful physiological information.